Our knowledge of kinetic energy has been thoroughly explored by the many equations surrounding this common mechanical property. Predicting collisions as well as their consequences has evolved from Newtonian mechanics to Lagrangian mechanics, two useful mathematical tools for all things physics. Yet, the mathematical formulas are merely the language of the universe and not its actual reason that those causal links evolve in such a way. There must be a physical process which explains why, from our stationary point of view, a moving object has more energy or simply interacts with our environment in a different manner. In this video, I will try to discover the emergence of kinetic energy through the fundamental properties of light and matter. First, let's remind ourselves of how objects interact with each other, but what we know as physical contact. When we see normal objects hitting each other because of their different relative velocities, the actual contact happens in an atomic scale. The electrons of the opposing surfaces of contact will come too close to one another and repel immensely when a microscopic threshold of some distance is met. The objects will transfer their kinetic energy spread throughout their body into this surface of contact. All physical contacts visible through the naked eye are thus electromagnetic interactions. When we take a closer look at a moving electromagnetic particle, there is no actual kinetic property. There is no universal counter setting its speed. The particle itself is always in its own inertial frame of reference, and so its added kinetic energy can only be seen by an observer in a different inertial frame of reference. To the point of view of a thrown baseball, it is the environment around it that changes velocity. Conversely, as stationary observers, we instead see the baseball change velocity from when it is thrown to when it is caught. How can electromagnetism encode this difference in perceived energy within moving matter? Before getting into visuals, we need to use the most fundamental formula, which includes all non-potential energies. This formula is called the energy-momentum relation and includes the rest energy of all matter as well as the energy added through velocity. Although momentum is considered velocity times mass in normal circumstances, we must not forget the Lorentz factor if we are to include all possible scenarios. We can rearrange it all to reveal a simplistic relation that will factorize a function of v instead of adding it as a standalone term. This relation would imply that the rest energy of matter is multiplied by the Lorentz factor as it increases in velocity in the point of view of stationary observers. This factor is incredibly small under normal circumstances, yet we will see later on that it is never insignificant. Now, we only need to understand why this Lorentz factor would emerge from electromagnetism. To do so, let's imagine a stationary charged particle in an empty space. For simplicity's sake, we will continue onward in 2 dimensions. Initially, its electromagnetic radiation is uniform in all directions. However, if we change the particle's velocity and examine its radiation after its change in motion, the properties of the radiation will change for a stationary observer. If its velocity is a good fraction of the speed of light, like 75% for example, then the radiation will visibly change wavelength and in turn change its energetic properties. The energy contained within electromagnetic waves is inversely proportional to its wavelength. This is a Doppler effect with electromagnetic waves. If we look at the spherical distribution of wavelengths, not only will they be different all around the particle, but the energy contained within them will also increase altogether. This is because the increase in energy of lesser wavelengths is stronger than the decrease in energy of greater wavelengths. If the particle would reach close to the speed of light, the extremely high frequency and dense electromagnetism would increase its total kinetic energy to near infinity, as predicted in all kinetic formulas, which accounts for relativistic properties. We can divide a sphere into open spherical sectors which emanate from the center of the Doppler effect. These sectors will each have their own wavelengths along their volume, proportional to the division of their volume dV by their exterior surface dA. The inverse of this division would then give the resulting energy level of each individual sector. To calculate the volume and the exterior surface of those spherical sectors, we need a spherical cap which engulfs the desired sector. Then, we subtract or add a cone which links the circumference of the cap to the center of the particle. We repeat this whole process a second time with a smaller cap. The overlap of the bigger solid is exactly the desired open spherical sector. A script made with R to calculate these measurements is available in the description below. Using the average of all energy levels, we will find the factor influenced by velocity that will multiply the rest energy of the particle. By varying the center of the Doppler effect, which would translate to varying the speed of the particle compared to the speed of light, the simulation will show that the rest energy is increased by the Lorentz factor. The precision of the Lorentz factor is dependent on the number of sectors which divides the whole sphere. We can see that although 10 sectors does not yield a factor close to the expected formula, 100 sectors has a mere 1% discrepancy at high velocities. 1,000,000 different sectors results in exactly the Lorentz factor with more or less 10 to the power of -8% of discrepancy. You may argue that such a Doppler effect is insignificant at low velocities, such as those we face in our normal lives. The Lorentz factor is extremely small even for things as fast as cars, jets, or space shuttles. Yet, the microscopic effect is emboldened by the enormous amount of rest energy in mass itself. If we isolate kinetic energy from this total amount of energy, we will see that the Lorentz factor -1 can be mistakenly seen as 0. The binomial approximation of v² over c² is, however, extremely precise, and so the resulting formula transforms into a familiar equation. Indeed, small increases in velocity compared to the speed of light is never negligible because of the incredible amount of energy stored within mass, which translates into greater kinetic energy. To recapitulate, the Doppler effect from electromagnetism increases the energy of any moving mass in the perspective of a stationary observer. This increase in energy of changed wavelengths therefore multiplies the rest energy by the Lorentz factor. As the total energy contained within rest mass is enormous, we can see measurable differences of kinetic energy even for slower velocities. From this equation emerges all other classical formulas that we use to predict collisions and the energy contained within moving systems.